Very good. So today we're very lucky to have Nikita Nekrasov all the way from Stony Brook, and he's going to tell us about some recent progress on quantum integrability and supersymmetry.
Thank you very much. With your permission, I'll remove my mask. I'm quadruple vaccinated in several countries, so totally harmless. So it's a pleasure to be back in Chicago after it feels like 6 or 7 years of being away. And it's a beautiful new building, so it's a pleasure to try it on. The topic of my talk is something I've been working on I would say, all my scientific career. So I will start with a few remarks which are very general, but then we'll move to more specific topics. So in quantum mechanics, we are familiar with the structure of what sometimes is called spectral triple. So you have the algebra of observables. You have its Hilbert space representation. So the algebra of observables, the observables will be represented as operators acting in the Hilbert space. The algebra is usually assumed to be a so-called C-star algebra, so you have a conjugation and the product, which is associative, and then the conjugation on the algebra becomes a Hermitian conjugation in the space of operators. And then there is a distinguished operator, Hamiltonian, which generates the time evolution. And so this structure is meant to represent the path integral, where we integrate over the maps of something one-dimensional. So it's time, or an interval, or a circle, which is mapped to the phase space. Now you can now, of course, imagine that this structure doesn't come with any classical picture, so it doesn't have to come from a path integral. But most of the interesting examples we know of do have a kind of a semi-classical description. Even the sporadic cases, you can, with some effort, embed as maybe as cosets, or we could relate to something which admits a quasi-classical limit. And so I will assume that exists. And so it means that there is some parameter in the problem which measures how far this algebra, which is non-commutative, yet associative, how far it is from a commutative algebra. So on the phase space, we have the ordinary functions, which we can multiply pointwise, and they will form obviously commutative algebra. But there is some structure which tells us that there is a way maybe to deform that structure to the fully non-commutative associative algebra. That's a Poisson bracket. So the reason why that structure gives you something non-commutative is that the observables, so they usually they're assigned to those specific moments of time. So when we compute the expectation value of a product of observables, so the observables correspond to maybe some functions on the phase space, which we order according to the time moments where we want to measure them. And because the time line is one-dimensional, there's a natural order. So it's simply the topology of the space of labels for the observables implies that makes commutativity very surprising. So let's put it this way. So because things here are ordered, there is no a priori, there is no reason to expect that the observables will commute. There's the time ordering. Nevertheless, there are some miracles where suddenly the algebra of observables contains a commutative sub-algebra. So quantum integrability so this is a situation when there is a sub-algebra inside the algebra for observables, which is commutative. So the operators from the sub-algebra commute. And so in this picture, it doesn't matter which one is first. The expectation value of the matrix element will not depend on the ordering or the time ordering for these operators. And that's very surprising, because as I said, that there is no way to move these operators one through another without going to some singular case where they sit on top of each other. So from the quantum mechanical point of view, the presence of such sub-algebra, and especially large commutative sub-algebra, so large in the appropriate sense, is very surprising. And as I will argue, the presence of such sub-algebra actually suggests that the system which you're looking at, which appears to be quantum mechanical, actually has a higher dimensional origin. That's my point. So at least, so in higher dimensions, the local operators, you can move around each other, and at least naively, so you can change the time ordering of operators without having them to sit on top of each other. So it doesn't mean that the result will not change, but at least it gives you some room for maneuver. Now, in order for this room to maneuver to be actually useful, you need some argument for why moving the operators at least a little bit doesn't change much the expectation values, or the expectation values of what of the objects of your interest. And this is where the supersymmetry comes in. So just the fact that if you start with, if you found some quantum mechanical system which is integrable, meaning that the algebra of observables contains a large commutative subalgebra, should make you think that should make you look for the extra dimension in the problem, and that extra dimension coming with some degree of supersymmetry. The supersymmetry being useful in the following sense. So supersymmetry gives you the the structure of gives you a grading on the Hilbert space, and the Hamiltonian is usually comes accompanied with another set of operators. I will call them Q and G. So these are, this would be, let's see, bosonic and fermionic, the even and odd parts, and Q and G are odd operators such that Hamiltonian is the anti-commutator of Q and G. So I'm describing this in the quantum mechanical language, but I will actually need this structure in field theory, which will look like quantum mechanics asymptotically, maybe in some large distance low energy limit. If you have that structure, and better yet, in quantum field theory, it's not just the Hamiltonian, which is the anti-commutator of two fermionic operators, but really the stress tensor. Sorry. And there are different ways of describing this. So I will describe it in a way that sometimes called twisted supersymmetry. So the supersymmetry you read about in textbooks has generators which are usually spinors in space-time. But if you work in flat space-time, which is what I will be doing for the moment, I can relabel the spinor indices. Sometimes I can relabel them so that one of the supercharges which actually become a scalar, and another bunch of supercharges can be organized in a symmetric tensor, just like stress tensor. And so if that's the structure, then inside the set of local observables, of the algebra of local observables, these are the operators, so which commute or anti-commute with the operator Q. In other words, the cohomology of the. So I forgot to mention that, of course, these odd operators should square to zero. So this is the part of the supersymmetry algebra. So in general, the Poincaré type supersymmetry has supercharges which anti-commute to translations in space and time. And if you're in quantum mechanics, you only have time. So the supercharges either anti-commute to zero or to the time translation. And if you go to high dimensions, then of course you have a bunch of operators, as many as spinors, and maybe more if you have extended supersymmetry. And then with extended supersymmetry, typically you can find an operator which will square to zero. So you can use that operator to refine the set of operators and find among those operators the ones which are annihilated by Q.
G is not Q Decker.
So so here the Hermitian conjugation is kind of tricky. So the dagger of Q will be one of the G operators. Actually, it will be like G not not. So this twisting, this relabeling of generators screws up the normal the Hermitian structure of the set of operators. But it's just a relabeling, so it's not, it doesn't, unless you start doing field theory in curved backgrounds, I'm not changing the theory. It's the same theory.
What is large in this case for the sub-algebra?
Oh, okay, good question. Thank you. Sorry, I forgot to say. So large means that you can actually characterize the states of the Hilbert space by the as a spectrum of this commutative subalgebra. So you can find there's large means that there is a basis psi lambda of the Hilbert space such that the vectors in this basis are characterized completely up to a phase by being the eigenvectors of all these Hamiltonians, of all these commutative operators. So lambda is a vector with as many entries as you have the number of generators, is a number of generators of that commutative subalgebra, and being large means that you can separate the states in the Hilbert space by the property that they are eigenvectors of this commutative subalgebra. And that's, of course, this might be maybe not. It's always difficult to give a good definition of what is actually what's quantum integrability. So you can imagine having actually some quantum chaotic system where the Hamiltonian is such that it's given an eigenfunction, eigenvalue of the Hamiltonian completely characterizes the eigenvector. So it might be not. So mathematicians usually like to impose some conditions on the dependence of these vectors on this eigenvalue. So maybe in the case of a continuous spectrum, you would like this to be kind of a smooth dependence, so that with discrete spectrum it's harder to define. But I will argue that all the systems that we know of with discrete spectrum, they actually can be embedded into some kind of continuous spectrum system where the continuity or smoothness independence of these labels can be formulated. So of course this is coming from, this intuition comes from the intuition in the classical case where the classical integrability is a property that you have the maximal set of functionally independent functions on the phase space which Poisson commute. And so there you have some tools of what does it mean to be functionally independent. So the derivatives of these functions, the matrix of second derivatives is degenerate, and so on and so forth. It's not. I mean, I don't have a very good definition, so that's why I put it in quote marks. If you have a parameter which sort of characterizes the deviation of your system from a free system, then it's hard. Then it's easier to explain that. Then, in some limit, the eigenfunctions are some product like plane waves, and so you just want to have the number of momenta which is needed to characterize the plane wave to be equal to the number of those Hamiltonians. But of course, it's not always possible.
Is locality something you can use to kind of distinguish? You gave this example of a chaotic
So
system.
locality in quantum field theory sense is often in conflict with the presence of this operator. So these operators are typically non-local. So if you think about like a spin chain, the best ways of, technically the most efficient ways of producing these operators, they don't respect locality.
But they're probably still nicer than the projectors on eigenvalues of the Hamiltonian.
Yes, of course. Yes, of course.
I don't know if there's a way to make this.
No, but part of this project is probably maybe a search for the actual the property of the systems which guarantees that these are nice systems. So my story continues in that way. So I'm trying to argue that if you do have a nice large sub-algebra, then probably your quantum mechanical system actually is secretly a two-dimensional, maybe high-dimensional theory. So that this one line is actually an approximation to the cylinder. Maybe as I will probably argue even in high-dimensional space. And then these operators hopefully they're local in quantum mechanical sense, but they're also local in a two-dimensional sense. And so then you can move them around in two dimensions. And what this property tells me is that if this is the case, then the space derivatives of my operators are actually Q commutators with some operators which are kind of supersymmetry descendants of local operators, and that means that the difference between these operators insert at different points of space-time. So this is now in space-time. Is Q of an integral over this density G along some path connecting X to X prime. And that means that, of course, not for all operators, but for the correlation functions of operators which only involve Q-closed operators, you're actually free to move the position of insertion without affecting the expectation value. And so that would explain why the correlation function doesn't change when you switch the order, switch the time ordering of those operators. I'm trying to repeat this argument. So to have some bunch of operators in one K O of X. All operators, and I assume that all operators are Q closed, including alpha and beta, then this correlation function is equal to this correlation function.
What distinguishes O from A?
Nothing. Just that these are spectators in my argument, and O and or are being moved around. Bad notation. Let me call them O. I just got tired of writing O. So the difference between these two expressions is something Q exact, and then the assumption of supersymmetry is that Q is a symmetry of the of a correlation function. So the expectation value of Q commuted with everything is 0. Difference between this and that is something which can be written as a Q operator applied to the product of O1 over K, then integral of G from X to X prime, and G for O alpha, G for O beta, and then product OK plus 1 O n. And that's the equals to 0. So that's this is the supersymmetry assumption. So armed with this very general, very silly argument, you can now look for some examples of where this can be actually realized and made into an actual tool. So historically, the first example of that was so the silly example so I'll take as the Hilbert space the space of L2 functions on n copies of a circle. But to make things a little bit non-trivial, I will quotient by the action of permutation of the group of permutations. So I have. So what this is the states of n particles on the circle, and the Hamiltonian will be just the sum so just n free particles. And we have a choice of course, we can look at bosons, we can look at fermions, and it turns out that things are interesting if you look at free fermions. So just the way functions are assumed to be completely antisymmetric. Okay, so then, of course, so this is obviously part of the sub-algebra, which is generated by the operators HK, where HK will be the sum of momenta to the kth power. So this operator is obviously commute, and diagonalize these Hamiltonians, and the eigenfunctions would be characterized by precisely n momenta. Momenta would be quantized because they are on the circle. You need to make some ordering of momenta because these functions are antisymmetric. So everything is trivial. You might say, what's the point? Well, the point is that this has a non-trivial deformation where let me start by adding an interaction term. So let me say that so the variable x has periodicity 2 pi. So I will put the repulsive interaction of this form. I think I keep forgetting. I think it's here. So now it's not immediately obvious, but again, this can be deformed. So there are some new dependent corrections. And so now you have a whole family of quantum integrable systems, so they all commute. The spectrum depends on mu, actually. Interesting, but not too complicated way. So, according to this paradigm, you should be looking for a high-dimensional origin of that quantum mechanical system. So what's the high-dimensional origin? Well, it turns out that this is related to a two-dimensional Young-Mills theory with gauge group UN. So let me just write the action of the Young-Mills in the first order formalism. And well, this looks completely bosonic, but okay, I need to speed up a little bit. So this can be made into a topologically twisted supersymmetric theory by adding a trivial term, which contains fermions which enter without derivatives. So what are the fields here? So the fields are a scalar, which is the adjoint valued. So gauge field, and the fermion psi, which is in this twisted notation, it's a one form. So it's one form adjoint valued. And the supersymmetry, the operator Q acts by mapping the gauge field onto the fermion psi. Psi transforms into the covariant derivative of sigma, which is d sigma plus the commutator. And sigma is transformed to 0. So this is actually, okay, on one hand you can integrate the fermion psi and then you integrate sigma, and you end up with the ordinary sigma and psi are out, then you get trace f mu squared 1 over g squared. So usual Young-Mills action in 2 dimensions. On the other hand, if you don't integrate them out, this action is actually a limit, and that was discovered by Witten 30 years ago. So this is actually, it's a kind of it's a limit of a 2D n equals 2, 2 supersymmetric Young-Mills theory. So the 2, 2 supersymmetric Young-Mills theory has many more fields. It has is complex scalar, so that this guy has the fermions of opposite chirality, which in this language would be two scalars actually, theta. And so it has a few more fermions and a few more bosons, let me put it this way. But it turns out that you can deform the Young-Mills theory by turning on the so-called twisted superpotential. So you add twisted superpotential of the form trace sigma squared. And so people are usually familiar with superpotential, so it's some kind of a chiral superspace interaction which generates potential for scalars and Yukawa couplings for fermions. In extended supersymmetries, there are different types of those special terms. So this one involves the scalar in the vector multiplet. And what you can do, I mean, the trick which Wheaton invented actually without realizing that, is that you can at a time maybe, you can introduce different parameters in front of the superpotential and its conjugate, T, and we call them T and T bar. This terminology with T and T bar was invented later, actually. So that's, and then you can take the limit which violates the naive reality, namely you make T independent from T bar and then send T bar to infinity. So this is the limit when T bar is sent to infinity and T is fixed. Since then, we've been doing those chiral types of deformations in many examples of theories, and this is mostly used these days in the context of the A model topological string. But anyway, so this is what he did, and what happens when you perform such deformation is that these extra fermions, chi and eta, as well as the conjugate scalar sigma bar, become effectively infinitely massive and decouple. And the original Young-Mills action is actually Q exact, so you can drop it, but the superpotential deformation produces, this is what is produced by that term. So this is actually, if you're familiar with two-dimensional supersymmetry, you'll recognize that this is actually the kind of a superpotential term. And this is another deformation. So this is adding a so-called zero observable and just smearing it over the space-time. So the zero observables are the ones which are annihilated by the Q operator. And so here we have plenty of observables which anti-commute with Q. So these are the ones which are built out of the scalar sigma. So any gauge invariant function, so this is, we only want them to be gauge invariant, will produce something which is annihilated by Q, and therefore its expectation value will be independent of the position of where it is inserted. And so this would lead to, to commuting Hamiltonians. And so if you take the 2D Young-Mills theory at its face value, and you study it on a cylinder, so 2D Young-Mills on a cylinder will be equivalent, just equivalent. So this is my time goes along the cylinder, and space is let me call the space coordinate y, so space is periodic. So this is actually, so this is equal to the quantum mechanics of n particles which live on the circle. That circle being dual to the original space circle. So what are these particles? They're actually eigenvalues of the holonomy of the gauge field around the space circle. So this can be conjugated by a gauge summation into a diagonal matrix. Diagonal exponential. And so I can insert here operators trace sigma squared, trace sigma cube, and so on. And they all commute, and I can characterize the states by fixing the eigenvalues of those operators. So trace sigma to the k will act in this basis of wave functions which are functions of x simply by operators which are the sums of kth powers of momentum. So, so here you can do this just essentially by trivial manipulation in path integral. It's essentially Gaussian integral. So you would not think that there is anything deep there. But first thing you can do, without spoiling the structure, that you have a two-dimensional bulk of the theory, which admits this structure with operators which can be moved around. You can introduce a line defect. So now we can add a line defect, which will be actually going along the time direction. So one line defect in 2 dimensions, essentially, it's a Wilson line. Now it's a Wilson line in a time direction. You can make it gauge invariant by either you work on a cylinder or on a torus, or you can introduce some extra quark states. So take the matrix elements between these quark states. Depending on the representation in which you take this Wilson line, you will get different types of interactions between these x variables. And so there is a choice of representation which will produce precisely that type of inverse sine square interaction. So this is taken in some representation. Some representation of the gauge group. So this is now slightly less trivial, because this doesn't map in any simple way to a free system. But using this two-dimensional picture, you can actually, if you want to compute, for example, the spectrum of this model, so the spectrum you can read off the partition, the trace of the time evolution operator, which will be essentially the path integral on the torus, and then you can use all kinds of surgery techniques we can do in two-dimensional theories to compute that. So so that's some use of that. But the more interesting story is that knowing something about these systems and the way they can be extended and deformed tells you that that theory has some deformations and generalizations. So this system has two kinds of famous generalizations. So this is, by the way, this is called Calogero Sutherland Moser system. So Calogero invented it first in the case of an inverse, so in the rational case when it was just 1 over x squared, and found that its integrable Sutherland found a way to solve that system on the nose, just it's a quantum mechanical system without fancy stuff. Moser explained its classical integrability, and then Calogero, the first one, found that there is a way to deform this while preserving integrability by putting here an elliptic function. So this is the Weierstrass. So it's double periodic function. So it's in addition to the space period which we had, there is also an additional period which can be kind of imaginary. So if you want this Hamiltonian to be Hermitian, so that the potential is real, you will take the second period to be purely imaginary. But the integrability of the system is an analytic property. So you can make tau to be an arbitrary complex number, and commutativity will still take place. So the spectrum of this model, in general, is complex valued. But once tau is purely imaginary, it will align itself into the real axis. So that's one generalization. So it means that there should be an elliptic version of 2D Young-Mills, which admits these line operators. And another generalization, which was found by Dutch mathematician Roizenaux, and independently by English mathematician MacDonald, who didn't even think about this ability. It's now called the relativistic Collatero-Moser system because its Hamiltonians are involve hyperbolic functions of momentum. So, and then there's some product. Some constant, and then sine squared. And there is also kind of a momentum operator in sinh. The same thing. So, so when you quantize, and you quantize by saying that P is still the derivative with respect to x, these operators become the shift operators. But they look like the quantization of the operators representing the energy and momentum in the relativistic system. So that's why it's called relativistic. Relativistic Collatero-Moser system. So if you followed my logic so far, these operators, they corresponded to polynomial invariance of the scalar in the vector multiplet. So trace sigma to k corresponded to an operator which had kth power of momentum. So the generalization where the momenta appear in the hyperbolic form would suggest that that this should correspond to something like trace of exponential of sigma. So we need some theory. So another version. The trigonometric hyperbolic. Of 2D Young-Mills, where so it would be natural to consider exponential functionals of the scalar. And so that guy, we of course know what it is. This is the three-dimensional Chern-Simons theory. So instead of the cylinder, if I replace this circle by torus, so just fatten it up. So that now it's a space circle which is being fattened up. And look at the Chern-Simons theory. Now it's a 2 torus cross time. So now in Chern-Simons theory per se, I don't have local observables. Because anything I can construct, I would construct out of the gauge field. The curvature of the gauge field, which looks like a local observable, is actually 0 by the equations of motion. So the only non-trivial things I can work with in Chern-Simons theory are line operators. And so these two torus, one direction I would call y and another I will call z. So the scalar in two-dimensional Young-Mills is really just the z component of the gauge field of the Chern-Simons theory. So what looked like a point on a circle, so the point here corresponds to the circle in the z direction in a three-dimensional picture. So that's, so if you collapse the z circle, then this circle collapses to a point, and that's what you see. But now the gauge invariant expression which you can assign to the circle would be the holonomy in the z direction. Again, taken in some representation. And so the basis, the totality of such holonomies is equivalent. So if you take all representations R, it's the same thing as to take all possible gauge invariant functions of sigma, where sigma is essentially A sub z. And so it turns out that the ordinary Chern-Simons theory, which is the kind of topological theory, so the limit which takes you from Chern-Simons theory to 2D Young-Mills is essentially the limit of infinite level. So you take a k to infinity, and in that limit, the set of all the relations between these observables which you have for phi at k essentially disappear, and that corresponds to the set of all Heisenbergs of sigma in 2 dimensions.
Why is this related to some relativistic limit?
Right. So if you again, there is a kind of a head-on approach when you just quantize Chern-Simons theory on the torus times time. So the phase space is when you read off the Gauss law from this and so on, will essentially be the so it's a modular space of flat connections, right? So it's a modular of flat UN connections on the torus, which so flat connections characterized by the holonomies around the A cycle and B cycle, which you can simultaneously diagonalize. So what is the phase space? So you have the variables x and okay, let me call them A and B. So this is the eigenvalues of the holonomies around the A cycle and B cycle. The holonomies are actually phases, so A's and B's are the logs. And so in the basis where so if I want my wave function, for example, to be a function of the holonomy in the y direction, as I did in the Young-Mills case, so that would be, let's say, so the wave function is a function of n periodic variables. And now, as Hamiltonians, I will take the invariance of holonomies in the z direction. So the Hamiltonians would be things like the sum over I from 1 to n, e to the I, call it L, so not to the level, bi. Okay. So these are exponentials of the phases which are the eigenvalues of the holonomy around the dual cycle. But this relation means that when I quantize, B becomes something like K, maybe 1 over K d by dA. And so these guys will act as shift operators acting on these guys. And so this expression, for example, before we turn on some defect which will produce this coupling constant, this is simply H1 plus H minus 1 in this notation. And this is H1 minus H minus 1. I'm not careful with the factors of I and so on. So the relativistic nature of the effects of quantum mechanics is simply the gauge invariance. The invariance are the large gauge transformations in the three-dimensional sense, which shift both the coordinate and momenta by some periods. You see, so B's are momenta for A's. A's are identified with X. This picture. And the fact that the gauge invariant quantities which you can write will be always some, they have to be trigonometric functions to be periodic and large gauge transformations, implies that your quantum mechanics will have this relativistic flavor.
When you say relativistic, does it mean that there is also some boost operator?
Well, yes, actually there is a boost operator. So what is the boost? The boost is the, so remind me, so this is the, yeah, so it should be the, well, the boost operator does not commute with translations in space and time. So,
Sure.
so I would not consider it in the, I would not add it to the list of conserved quantities.
Yes, but is the Lorentz algebra realized in any way on this?
Yes, but you can realize you can realize it. You can add it as well. Yes, it's some. It might be a holonomy in some mixed direction. So if you have the A cycle, you have a B cycle. So the holonomies in the B cycle are the conserved quantities. So they realize the momentum and energy. The holonomies in A cycle is what you act on. So this is how your wave functions are represented. Maybe there is some mix. So maybe it's in the holonomy in one direction in the specific representation. I don't remember it off the top of my head, but there's definitely a boost operator. All right, so then just as in two-dimensional N.Lee's case, you needed to insert a line defect to produce the interactions. In Chern-Simons theory, you can also insert this defect. Again, it will be a Wilson line in the t direction. And so, that will introduce this non-trivial dressing of the naive of the usual energy and momentum, which will correspond to the interaction between these particles. Not surprisingly, this finite dimensional system with relativistic invariance is actually a subsector of a quantum field of a field theory. So these are actually it was realized soon after Rosenars introduced this that this actually describes solitons in Sine-Gordon theory. So it's n-soliton sector in relativistic field theory, and the number of solitons was conserved by classical dynamics. What's non-trivial is that this survives quantization. So you don't need to have the full quantum field theory to make sense of this quantum mechanics. All right, unfortunately I'm out of time. I will say two things briefly. So I didn't explain how you get the elliptic version of 2D Young-Mills. So that you do it also by replacing the circle of Young-Mills theory by two torus, but this time you view these two torus as elliptic curve, not as a topological torus. Because you need this parameter tau to appear somehow, the complex structure. And then it was realized, so that was in my PhD thesis in 1996, that you can actually combine, you can actually do both. You can do this and this together. And So that's here it was known on the integral side to the elliptic function. Here, so you can combine both by writing this now on the product of elliptic curve with the parameter tau and some two-dimensional space, which is kind of topological, where you write this non-Lorentz invariant action, where dz is a holomorphic differential on the elliptic curve. And this looks very unnatural as an action of the theory because it uses explicitly coordinates on space-time. But this is actually the way I introduced it was this was an observable if you again dress it with a term like psi in the Yang-Mills theory in n equals 1, d equals 4 super Yang-Mills theory. So the idea is that two-dimensional n equals 2, 2 super Yang-Mills theory is actually dimensional reduction of the minimal supersymmetric theory in 4 dimensions. And so out of 4 supercharges of the 4-dimensional theory, you can select one which annihilates a specific component of the gauge field, like a light-like component, which if you do the weak rotation will be a holomorphic component in fact, anti-holomorphic component along the 2 dimensions out of 4. So this scalar sigma in 2 dimensions actually originates from the 0, 1 component of the gauge field along the 2-dimensional torus. And so this action is a reduction of that, and the supersymmetry which was needed to support that action is a kind of reduction. It's actually a reduction of n equals 1 equals 4 supersymmetry. So the trouble with this theory, was immediately, I realized immediately, of course, that it is not gauge invariant. So usually we say that what multiplies the Chern-Simons action has to be an integer, because there are large cases of transformations which can shift the Chern-Simons form by closed 3 form, which is not exact, which has nevertheless integral periods. So if you write such an action on the form manifold of the form of the product of elliptic curve and some Riemann surface, this action will be anomalous in the sense that under large case transformations it will shift by k times 1 period of differential and 1 where omega 1 and omega 2 are the periods of the holomorphic differential. So holomorphic differential has 2 periods, and the ratio is precisely this parameter tau, which we needed for the elliptic version of the Moser system. So if the elliptic curve is not degenerate, then this parameter is not a rational number. It's a complex number. So you can adjust the level k to make sure that at least half of those periods will be an integer. So in the exponential, this will be well defined, but you cannot adjust them in such a way that both of them will be an integer. So in 1996, I stopped there because, so I said that maybe by going to the theories with extra matter fields, you can cancel this anomaly somehow. this anomaly has to do, in another picture, it has to do with the fact that the modulus space of flat connections on the two torus is not a string manifold. So the partition function of the theory would compute the elliptic genus of that space, and it will not be modular invariant because this is not this is an anomaly, which spoils it. But you could cancel this anomaly by adding extra matter fields, and so maybe that was my hope, that maybe that one can make sense of it for more general theories. Now in 2013, that theory was rediscovered by Kevin Costello, who used exactly the same idea to produce it, but instead of working on the elliptic curve, he just said, okay, I will just work on the cylinder or on this flat space. So he simply said that he will work on the space for which this differential curve has only one period, doesn't have a second period. So it doesn't help. So in that way, he loses the relation to those systems which exist, but you gain the possibility of just treating this theory as a perturbative quantum field theory. And so since then, it has generated a lot of follow-up, including the realization of an important object in the business of building quantum two systems, the so-called R matrix, which so this is the solution of Young-Baxter equation with spectral parametry. So in this way, many integrable systems can be treated the way the largest models were treated previously by the ordinary Chern-Simons theory. But the true progress actually came from, I would say, I mean, this is progress of sorts because that allows you to systematize a lot of known facts. But the progress in the sense that it leads to discovery of new models, which were not previously known, came from another approach to, from another kind of generalization of that story, where instead of where we started to play with different models with that amount of supersymmetry, but different matter fields. So that was the route which I said that was needed to make sense of that model in the elliptic case. And it turned out that once you go away from the pure Young-Mills theory to Young-Mills theory with matter fields, you get access to all kinds of non-trivial systems, including the spin chains. So for example, SU2 spin chain. So Heisenberg. Spin chain with, so you have L spins, spins 1/2, let's say, on the periodic, arranged in a periodic fashion. So the Hamiltonian, you can fix the total, the projection of the spin so on the third axis, on the z-axis. So that gives you a finite dimensional. So it's a finite dimensional space, of course, which can be very large. So the dimension is L choose M. And the claim is that this is this is the quantum mechanical system, which nevertheless is a subsector of a quantum field theory. So it's a two-dimensional, in fact, it's a 4,4 softly broken by a certain twisted mass term to n equals to 2. So it's a theory, it's a gauge theory with gauge group un. So n is relative number of spins pointing up with L fundamental hypermultiplets. And so this theory, it's an example of a so-called quiver theory. So we usually denote it in this way. So this n in the circle means that you have un gauge group, and L in the square means you have a number of fundamentals. And this diagram corresponds to a diagram which consists of a single point, which is known as the A1 Dynkin diagram. And A1 is SU2. So in this theory, you can compute the effective twist superpotential. This is a one-loop computation, which is exact. And the equations for the vacua, for the expectation values of twisted Keil ring operators, which you get from that computation, will match precisely the Bethe ansatz the Bethe equations for the spin chain. So Bethe equations describe the vacua of the theory. So if instead of if you take now arbitrary Dynkin diagram, so here I drew the Dynkin diagram of a fine I think it's G5 hat type. So that would mean that, well, you just replace every node by a gauge factor. And also introduce some fundamentals for each node. It's a straightforward generalization on the side of the gauge theory, but so that you can compute the equations describing the vacua, and then you'll get a spin chain, and sometimes you get spin chains which condensed matter physicists never looked at them before. So because, for example, here you get the spin chain for which the spin group is actually a Kac-Moody group. And before this was done, people didn't know those existed. And so now some of them are related to quantum hydrodynamics. This was realized not so long ago, but some of them are completely new. And so those systems are kind of challenging to describe in that language, but for systems which correspond to the Dynkin diagrams of fine dimensional groups, there is a way to relate this approach to that approach using string theory dualities. So to conclude, I would not say that we have the complete story and complete classification of the quantum integral systems, but we have the understanding that in majority of cases they come together with the some supersymmetric gauge theory in 2 and maybe higher dimensions, but at least with n equals, at least with two-dimensional superpoint current variance. And that's a useful point of view because it gives, sometimes it gives the new systems, sometimes it gives you the way to compute the eigenfunction, not only eigenvalues, not only the spectrum of the Hamiltonians, but also sometimes it gives you even constructs a way of computing the wave functions, so the states. And whether this can be used for systems which are obtained by deformation of integrable systems, like away from the more ergodic systems, I don't know. But at least these are interesting islands in the landscape of all theories which we can think about. So let me stop here.
quick questions?
Yes.
Do you think any integrable lattice model can be constructed in this way?
I think so, yes. So the challenge, so far the most challenging systems which I encountered, for which I don't know a good supersymmetric gauge theory description, believe it or not, these are the systems which were found by people working on supersymmetric Yang-Mills theory, and these are the Bethe equations which describe the spectrum of anomalous dimensions of n equals 4 super Yang-Mills. So, you can get a kind of a tricky quantum mechanical system by taking a 4-dimensional theory and compactifying on the 3-sphere. So, if you take n equals 4 super Yang-Mills on 3-sphere, so that's quantum mechanics, and you can truncate to the, well, you can look at the low energy spectrum, so it will be kind of approximated by some finite dimensional quantum mechanics, and there is an evidence, and people sometimes claim with victory, that in the planar limit, this is actually an integrable quantum mechanics. So people write the equations describing the spectrum of dilatation operator, so spectrum of anomalous dimensions, and they look like the Bethe equations for the superspin chain, now for the essentially SL4/4, so this is a superconformal group. So Bethe equation, being able to write Bethe equations means that your symmetry enhances to the so-called Yangian algebra. So it's an infinite dimensional dressing. So here, for example, I had SU2. So SU2 has 3 generators, but it turns out that there is an action of the infinite dimensional algebra in this finite dimensional space, which contains a very large commutative sub-algebra, which are the integrals of motion. So so people write the Bethe equations for the Yangian of the superspin chain, and superspin chain per se does have a dual gauge theory description, so you can write the Dinky diagram for the superalgebra. It's not a problem. It's a little bit so such models will be slightly farther away from the softly broken equals 4,4. So those are 2,2 theories, which are far away from 4,4 locus. But then the Bethe equations, which people like Bizert et al. Wrote, they contain the so-called dressing factor, which spoils the relativistic invariance. I mean, the certain property of the metrics of those models, which is lost in these theories. And the main property which is lost is that the equations which describe the spectrum cannot be written in this form. They don't have a single potential from which they all derive. You see, here the non-trivial part, which I didn't stress, was that you have many equations describing, because you have many variables. The scalars have many components, but even though you have many equations, they have certain integrability property themselves. Namely, they can be organized as a logarithm, as the logarithm of those equations. Essentially, they are the components of the exact one form. It is closed one form. So there is a potential which, in gauge theory language, is a twisted superpotential. But these equations don't have this form. So if I write them as phi I of a bunch of sigmas, then there is no way to choose a coordinate system for which these mixed derivatives will be symmetric. That's this dressing factor doing. And this is related to a peculiar property of that particular class of spin chains, for which are based on the superalgebras of this SLN/N type. these are funny algebras which, if you take a single model with this supergroup with a target space, you don't need a Vesuvian term to make it conformal invariant. So it has some special features. And so it looks like these equations could be interpreted in the language of now not 2,2, but 0,2 supersymmetry to two dimensions. So this can be further broken, but what's lost is some kind of a sense of naturalness. So in all the previous cases, there was a miracle of naturalness in the sense that the textbook examples of quantum integrable systems were mapped to the textbooks examples of supersymmetric gauge theories, even though it's different textbooks written by different people, different points in space and time. Somehow there was a common naturalness. But this guy is, so if you try to map this to some 0,2 theory, it's very ugly. So at the moment, this is my main challenger to this concept. But recently, I was looking at there's a kind of a truncated version of that story, which is called the fishnet theory, and which still has the same feature. So there is a dressing factor which spoils that symmetry, and I'm close to getting some kind of a dual 0,2. Maybe actually I made the blunder. I keep forgetting. There is a certain code of conduct. So you write 2,0 for 6-dimensional theory and 0,2 for 2-dimensional theory, so or vice versa. So this is 2-dimensional. So there is a candidate for that 0,2 tool, but which is less ugly than the one for the one that was for. But I'm still not quite satisfied. There are metrics, so maybe the last piece of advertisement. So together with my postdoc, M.Dedushenko, we found the way of embedding the R matrix in this world, in this using the so-called supersymmetric interfaces. So these are interesting ways of making some of the parameters of your theory space or time dependent without breaking completely all of the structure, which allows you to imitate some of the constructions of spin chains and related systems. So maybe, but so far it uses that structure. So these are natural in theories with 8 supercharges, which are only broken to lower supersymmetry by some background fields. But in principle, you can go get those defects in the even in quantum mechanics with the with 2 supercharges, they are possible. But we haven't mastered it completely. What I mean is, so you see, if you think about quantum mechanics, like corresponding to Morse theory, so you have a minimal supersymmetry, which is associated to some real potential. You can actually make this potential to depend on time, and so that will give you a kind of an interface when you may begin with one Morse function at the minus infinity, another Morse function at plus infinity, and then the vacuum will undergo some transformation going from one to another. So in the more complicated cases, these transformations can be arranged into the Young-Baxter structure. That's the story. Okay, so I apologize for going over time.
If there are any more questions, maybe people can ask Nikita after we're done. So let's thank Nikita again.